Hi, this is John Carpenter. I'd like to thank the organizers for making this presentation for the conference. I'm going to focus today on fundamental mechanisms of protein aggregation and stabilization during freezing, drying, and solution and at interfaces, and I also will provide some practical examples of why it's valuable to know these mechanisms. These are many of my collaborators I've worked with over the years on some of these more mechanistic studies. And here are the topics we're going to cover today. But let's start with the practical example. These are two case studies. These are real studies from industry. In the first case, monoclonal antibody bulk drug substance was thawed. It was very cloudy upon thawing due to protein precipitation. If the precipitate was collected by centrifugation, IR spectra could be taken, which showed the protein molecules in the precipitates were completely native. If the thawed solution, uncentrifuged, was allowed to stand for a few hours at room temperature, the precipitates dissolved and the protein molecules went back into solution. The second case is quite a bit different in the end. The solution was cloudy upon thawing, and if it was let to sit out at room temperature for a few hours, the protein molecules did not go back into solution. And if the precipitate was collected by centrifugation and examined with infrared spectroscopy, the spectra indicated non-native protein molecules as well as a high content of intermolecular beta sheet, indicating the protein molecules had irreversibly aggregated. So reversible precipitation in case one, irreversible precipitation and aggregation in case 2. So for these two cases, in which would the inclusion of 0.3 molar sucrose reduce the amount of precipitation? That is, in which case would the addition of this sugar be an effective formulation strategy? And here are the answers that you can choose from. We will go back over this later after we go through some of the mechanisms that are most relevant. But please note answer E, which is seemed to be very common in the industries. We don't really know the answer till we hire a bunch of consultants and do further extensive root cause analysis. However, I hope to convince you that by knowing mechanisms, you can say right away in which case sucrose would be a good formulation strategy. So let's start by talking with protein stability in solution and about how strongly binding ligands affect thermodynamic stability. This is called the Wyman linkage function that says if a ligand binds more to one state than another, that state with the bound ligand will be favored. In terms of protein stability, you can see here if we have the native protein going to the denatured state, if we add a ligand to the native protein that binds very strongly, the barrier between the native protein and the denatured state goes up a lot because ligand binding to a protein state lowers the free energy. By lowering the free energy, you favor that state, but in our example here, by lowering the free energy of the native state and not the denatured state, we get a much larger barrier between native and denatured state. And this is called the Wyman linkage function. In terms of practical use of this mechanism, here's an example with heparin, stabilizing fibroblast growth factor. Heparin binds very strongly to the native state, but not to the denatured state. And depending on the weight ratio, you can see a large increase in the apparent melting temperature for this protein. But there are many stabilizers that are not acting by binding strongly as ligands to the native state. These are what we think of as non-specific stabilizers like sucrose. These compounds essentially stabilize everything, all proteins. And the person that figured this out was Professor Serge Timoshev, our late friend and colleague, who worked for many years to understand the interactions between non-specific stabilizing additives like sucrose and proteins. And this is essentially the mechanism he defined. It's called the preferential exclusion mechanism. So in this case, if we have a stabilizer such as sucrose with a protein, and we do some studies, we find that the protein has a hydration shell, but there's a deficiency of the stabilizer around the protein compared to the outside. So in thermodynamic terms, this is a negative binding. So the negative binding means in the presence of the stabilizer, as shown here, the protein chemical potential increases. So preferentially excluded solute with the native protein increases the chemical potential of the protein. If that's all that happened, this would be a destabilizer. But the degree of exclusion depends on the surface area of the protein exposed to the solvent. So with the unfolded protein, we have a much larger level of preferential exclusion, which means a much larger increase in chemical potential. So with the native state, excluded solute leads to a little increase in chemical potential, whereas with the denatured state, we get a much larger increase. The net result is a large increase in the free energy of unfolding. Another way to look at this is from the principle of Le Chatelier that says if something perturbs the thermodynamics of a system, the system will tend to minimize that. So in this case, preferential exclusion increases protein chemical potential. The system will favor the native folded protein because the surface area of exposure to the solvent and the degree of exclusion is much less for the native than the denatured protein. In practical terms, we see this as an increase in free energy of unfolding. These are data for granulocyte colony stimulating factor. With guanidine unfolding, as you increase sucrose concentration, you increase the amount of denaturant needed to unfold the protein. Similarly, with thermal unfolding, with heating, the more sucrose you have, the higher temperature you have to go to the unfolded protein. And this applies to inhibition of aggregation. When proteins aggregate, they have to go through a partially unfolded state, referred to as N star here, which then it interacts with the neighbor, potentially can form clumps that make aggregates. If you do this in the presence of a preferential excluded solute, the surface area for N star is greater than N, so the net barrier between these two states increase. So the activation energy for aggregation will go up in the presence of compounds like sucrose. And again, practically, we can look here, this is GCSF loss of monomer during days of incubation at 37 degrees at pH 7. And if you have higher and higher amounts of sucrose in the solution, there's less and less aggregation. An indication of the effect of sucrose on the level of N star is shown here. N star will have hydrogen deuterium exchange occurring at a faster rate than the fully compact native state because N star has more solvent exposure. And looking at H to D exchange, in the presence of zero molar sucrose, you get this amount of change in an infrared spectrum signal that's indicative of exchange. With more and more sucrose, you get less and less exchange because sucrose is reducing the level of this aggregation component N star. And this is all summarized here. The native state going to a partially unfolded state, this structural change is a key component of aggregation. But there's a second governing factor, and that's the intermolecular energetics, which are often indicated by a measured parameter called osmotic second virial coefficient. The main component playing a role here is charge-charge repulsion. Therefore, pH is a critical parameter governing protein aggregation. And here's an example of the importance of the so-called colloidal stability. Again, looking at the protein monomer loss as a function of time at pH 7. In this experiment, you can see it here, sucrose slightly inhibited that. For this experiment, the important observation was benzyl alcohol greatly accelerated aggregation loss of monomer at pH 7. The reason for this is that benzyl alcohol causes a partial unfolding of the protein, which then fosters a high level of aggregation. Interestingly, well, first off, this can be partially blocked by sucrose, which inhibits some of that unfolding. But at pH 3, in the presence or absence of benzyl alcohol, the protein doesn't aggregate at all. That's because the protein's highly charged at pH 3, has its native structure, but the high charge keeps the molecules from interacting very well. Benzyl alcohol will perturb protein structure at pH 3, but the high charge inhibits aggregation. I wanted to have one little aside here about heating studies. Just keep in mind, when you have a heating study, you get both unfolding and aggregation for most of the molecules we work on. So either the free energy of unfolding, the native state stability, and our interactions between molecules can be the governing effect. So if you're doing a study, like say across pH, you may find the impact of pH at both steps, and that can help you overall find the optimal pH for a protein. If we put sucrose in the formulation, it most likely will influence this step by increasing the native state stability of the protein. Excuse me. So during freezing, we basically are forming ice, and the protein is in the non-ice phase. And protein aggregation will occur because proteins are perturbed by the various stresses that occur during freezing. Also, the high salt will favor intermolecular interactions. And so the degree of unfolding during freezing can be impacted by the native state stability as well as colloidal stability, or the aggregation. And any unfolding that occurs during freezing obviously will contribute during freeze drying. So how does the protein get stabilized by additives during freezing? Well, during freezing, the protein goes to the non-ice phase with water, unfrozen water. So essentially, everything's still the same as it would be in unfrozen aqueous solution, and a preferential exclusion mechanism applies. And so the degree of protection during freezing depends on the initial bulk concentration of the additive, just like it does with excipients in non-frozen aqueous solution. Here's some practical advice for freezing. Choose your buffer carefully. You want to make sure the buffer you choose does not have a large freezing-induced pH shift. And the buffer that's most notorious for these pH shifts is sodium phosphate. During freezing, the dibasic salt of the buffer can crystallize, and that crystallization can leave you with pure monobasic sodium phosphate in a pH down to pH 4 or so. The magnitude of the crystallization depends on the solution conditions, the temperature, and all the handling. So in general, using sodium phosphate, it should be avoided because you can get some surprises sometimes. For example, shipping of a frozen solution can cause buffer salt crystallization that you didn't see without shipping. During freezing, to maintain stability, having the appropriate pH is important, and also if you have stabilizing ligands, that's great. Non-specific stabilizers are often needed, like sucrose or trehalose, and it's been shown in numerous studies that non-ionic surfactants are also important to reduce aggregation, in this case most likely by reducing protein interactions with the ice-water interface. What about during drying? Well, now we have a completely different situation. As we dry a protein, the water molecules that hydrogen bond to the surface of the protein are removed. And this fosters protein unfolding. It may be also causing new intermolecular and intramolecular bonds to occur. And when you have unfolded proteins in a dried powder and you add water, there's a competition between molecules for refolding and aggregation. Also importantly, if you have unfolded protein molecules in a freeze-dried formulation, the storage stability of that product can be compromised. So how does additives like sucrose and trehalose protect during drying? Well, during drying, you literally strip off the hydration shell of the protein. At the water contents we have for a lot of lyophilized protein products, there's no water left around the protein. So we're not trapping water around the protein with the sugar. Instead, as the water molecules are removed, molecules like sucrose will hydrogen bond to the protein in place of the lost water. Now, for this to occur, the sugar has to remain amorphous. And the amorphous sugar is important because that allows the sugar to interact with the protein. If the sugar crystallizes, that can occur. But just having an amorphous formulation is not adequate because large polymers like dextran fail to protect proteins during drying. They stay nice and glassy, but they're too large to hydrogen bond effectively. And here's some examples of what this means in terms of protein structure. You can use an infrared spectroscopy to look at the protein secondary structure by observing spectra in the liquid and the dried state. So for this protein, interferon gamma, this is a second derivative IR spectrum. This dominant band here is due to alpha helix. If you dry the protein without any additives, you get this great perturbation of the spectrum indicating protein unfolding. And if you rehydrate that sample, you get this new band due to intermolecular beta sheet. This sample had about 18% aggregation after rehydration. In contrast, if you dry with sucrose, you retain a large degree of the native-like spectrum indicating protein unfolded is inhibited. You never get a spectrum that exactly matches the one in aqueous solution, because in the dried solid, the loss of water itself impacts some of the spectral qualities. If you rehydrate this sample, you have a very tiny new band here for intermolecular beta sheet. This only had about 5% aggregation. Contrast what sucrose can do for structural retention to what happens with dextran. This is dextran and actin freeze dried. Here's the aqueous spectra with the dotted lines for actin. As you dry it with dextran, note that we get no indication of retention of native structure. So dextran makes a nice glass, but it's not effective at hydrogen bonding to the protein in place of the lost water molecules. Such interactions are critical for real-world storage stability of freeze-dried formulations. This is look at an interleukin-1 receptor antagonist. Turbidity after rehydration, which is an indicator of aggregation, goes up tremendously as a function of storage time if there's no sugar present. But as sucrose is included in the formulation, you can completely inhibit turbidity increases. Similarly, chemical degradation, in this case shown by cation exchange chromatography, which is indicative of deamidation, can be greatly inhibited as you have higher and higher sugar concentrations. So the glass transition temperatures of all these formulations were about the same, and the values were all above the storage temperature. The key factor here is the native molecule retention was better as there was more and more sucrose in the formulation. Here's another example showing the impact of both glass transition temperature and proper stabilizing additives. This is a interleukin-11 study. In the presence of the disaccharides, the native protein structure was greatly retained. In the presence of the polymer hydroxyethyl starch, there was no stabilization of the structure. But the starch gives a very high glass transition temperature. So just starch alone does not inhibit aggregation during storage. Disaccharides alone are fairly effective, but at 60 degrees, not great. And then if you have both the polymer to increase the glass transition and the disaccharide to stabilize the native structure, you get outstanding stability of this protein. Almost no aggregation after 9 months at 60 degrees storage of the dried formulation. So overall, when we think of compounds like sucrose, the mechanisms of stabilization can be through the Timoshev mechanism. If we have strong binding ligands, it can be through the Wyman linkage function. During freezing and freeze-thawing, those same mechanisms apply, but during dehydration, we have the water replacement mechanism occurring. And during storage in the dried solid, the important factors are retaining the native protein and having a glassy matrix. So now let's go back to our two case studies. Case 1, remember, was reversible precipitation of the protein during freezing. And case 2 was irreversible aggregation due to freeze-thawing. Excuse me. During case 1, if we added sucrose, it would make it worse, actually, because sucrose increases the chemical potential of the protein, which means it reduces solubility. In case 1, the protein's irreversibly precipitating because freeze concentration is causing the protein to exceed the equilibrium solubility in the solution. Adding sucrose will reduce solubility and make the freezing-induced precipitation worse. Whereas in case 2, we have a aggregation occurring because the protein's perturbed by freezing and the unfolded molecules are coming together to aggregate. In this case, adding sucrose would help because it can actually effectively reduce the unfolding of the molecules and the subsequent aggregation. A bonus question to think about, what happens if we have a strong binding ligand? This actually helps in both cases. In case 1, a strong binding ligand increases chemical potential, which leads to an increase in solubility. Excuse me. Whereas in case 2, a strong binding ligand stabilizes the native state, which leads to less irreversible or less unfolding and irreversible aggregation. So knowing mechanistic insights into how things work can be very helpful to solving these practical problems. So now let's switch gears and talk about what happens at interfaces. Often if we do studies like agitation studies, this is data, these are images of particles formed during agitation of a monoclonal antibody solution. You see these particles that look like bits of film that have been kind of crushed up. Excuse me, that's exactly what they are. If you imagine this soap bubble being an air bubble coated with the protein film, if you pop that bubble, you end up generating a lot of these particles. And the reason for this is proteins form films at interfaces. Here's a photograph of one of those films being drawn up from the air-water interface. Here's photographs of an air bubble with protein forming film and then chunks at the surface. And as you compress the bubble and expand it, you can knock those pieces off. So what happens is the film formation is the first step in interfacial induced aggregation or particle formation. That film can be disrupted by mechanical forces like compression and dilation of the air-water interface, bubble popping. Absorbed layers can be scraped off, and there may be multiple interfaces like air bubbles and silicone oil in a syringe. And any kind of mechanical force, including shock from dropping, can dislodge that film and particles. And here's a very nice early study that demonstrated this. This is looking at a monoclonal antibody at the air-water interface, and they did a simple thing. They just had a needle that would rotate, and each rotation it would rupture the air-water interface and break this film. Excuse me. And what they found is that rupturing led to a high level of light scattering due to particle formation, which could be inhibited by compounds like polysorbate, which are very effective at inhibiting the absorption of protein to interfaces. We've seen similar things with proteins at the silicone or oil-water interface, where the rupture of the interface leads to aggregation, and if you have surfactant, you can inhibit that. The difficulty we have is interfaces are everywhere in the life history of protein products, from manufacturing to shipping and storage to delivery to patients. And during manufacturing, before the last filling step, there is a 0.2 micron filtration, which is very good for removing particles. Unfortunately, the pumps that are used afterwards often generate more particles, and those particles will be delivered to patients unless a filter is used during administration. So oftentimes, if people have particle problems, such you see here, visible particles in a pre-filled syringe, the filling process is to blame. And this occurs because of numerous stresses. There's interfacial stress because proteins can absorb to the walls of the pump, either peristaltic tubing or the walls of a piston in a cylinder, and be scraped off or ruptured. Particles can shed from pumps material. There can be cavitation, particularly in rotary piston pumps and with valve action and time pressure filling. And importantly, for time pressure pumps, the pressurized solution, when it goes into the vial or syringe, will have outgassing of bubbles, which leads to more interfacial stress. Well, here's one example from peristaltic pump filling of a protein intravenous immunoglobulin. 3 different brands of tubing over a large volume of pumping with 10 mil aliquots taken. Microparticle levels vary depending on the tubing. This one brand of tubing, Pharmed, results in the fewest microparticles. Nanoparticle levels vary also, with the Pharmed tubing leading to the most nanoparticles. Interestingly, if you do a post-pumping stress, such as agitation, the solution pumped through the Pharmed tubing makes the most microparticles during post-pumping stress, and the thought is that's because nanoparticles that were formed during the pumping itself causes a lot more microparticles. And you can see that nanoparticle levels actually decrease during agitation, presumably by agglomerating together to make new microparticles. These results show mechanistically the roles of different particles formed during pumping, during post-pumping stress. They also point out that it's important to use proper methods to study protein particles, such as flow imaging and nanoparticle measurements. Measurements made by light obscuration would often miss these kind of effects because light obscuration is fairly insensitive to measuring protein particles. Okay, I wanted to give one last example, and this is trying to bring a lot of things together. And looking at the roles of conformational and colloidal stability on agitation-induced aggregation of a protein. And in this study, the protein was agitated and recovery of monomer was a measurement of aggregation. So as monomer levels go down, we're losing protein to aggregate. So at pH 7, there's a modest loss of protein to aggregates. At pH 3, this is almost completely inhibited during agitation. And at 5 and 6, you get a little bit more aggregation. If we correlate these results to measurements of colloidal stability, B22, what we see is at pH 7, we have a modestly positive value, meaning charge repulsion. At 3, the value is much more positive, and that charge-charge repulsion is inhibiting aggregation during agitation. Whereas at pH 5 and 6, we're slightly negative or almost zero, which means there's very little repulsion, and during agitation, protein molecules readily come together. So for the pH effects, colloidal stability seems to play a role even during agitation. If we look here at formulation effects, at pH 7, if we add polysorbate, we can completely inhibit monomer loss due to aggregation because the protein is inhibited from adsorbing to the air-water interface, and it's really not anything to do with the intermolecular interaction energetics. If we add salt, we lose a lot more protein, and if you look, that's charge-charge repulsion is lost in the presence of salt. We go to a negative value of B22, which means intermolecular interactions are favored. So charge shielding by the salt will promote aggregation. The really interesting results are what we get with sucrose. Sucrose, which is a really good conformational stabilizer, for this protein is a colloidal destabilizer. That is, sucrose favors intermolecular interactions, and the net effect of that practically is sucrose promotes protein aggregation during agitation. Even though it would stabilize the protein in solution, by favoring protein intermolecular interactions, sucrose destabilizes the protein formulation during agitation. So it's important to consider the actual stress against which you're stabilizing a protein. And in this case, obviously, polysorbate is the best stabilizer. Okay, let me conclude and say that we know in bulk solution that both conformational and colloidal stability are important for governing aggregation of proteins. And by stabilization with additives can depend on specific ligand binding through the Wyman leakage function, for example, or nonspecific stabilization through the Timoshev mechanism. This also applies during freezing. Whereas during drying, as we strip the hydration shell off the protein, water replacement is the mechanism. And finally, when we have interfaces, interfacial stress, particles are formed because films of the protein form, and any kind of disruption in that film will lead to particles in the bulk solution. And surfactants are quite helpful at inhibiting this, but obviously with modern research we have to be aware that surfactants cause their own problems in particle formation due to degradation. And finally, read the literature. The newest literature is critical to keep up with, and the old literature back even decades ago has very important fundamental information. Well, I thank you very much for your attention. If you have any questions, my email is given at the beginning of this presentation. Please feel free to contact me. Take care.